Hello everyone and welcome back to our math classroom. Let me begin with a curious question. Have you ever tried to expand 99 to the power 3 or 101 to the power 6 without a calculator? Feels impossible, right? But don't worry, mathematics gives us a neat shortcut. Now, let's talk about how to actually get those mysterious coefficients. Enter Pascal's triangle, a triangular arrangement of numbers that encodes all the coefficients we need. It starts with 1 at the top. Each new row begins and ends with 1, and every inside number is just the sum of the two directly above it. For instance, the fifth row reads 1, 5, 10, 10, 5, 1. These are exactly the coefficients of bracket open a plus b bracket close to the power 5. So the triangle not only looks pretty, but it also hides the DNA of binomial expansions, symmetry, increasing then decreasing coefficients, and exactly n plus 1 terms. We define and choose r as n factorial divided by r factorial into bracket open n minus r bracket close factorial. Now, let's formalize this. We denote coefficients using binomial coefficients. We define and choose r as n factorial divided by r factorial into bracket open n minus r bracket close factorial. Symbolically, binomial nr equals fraction numerator n factorial over denominator r factorial into bracket open n minus r bracket close factorial. This gives us the coefficient of a to the power n minus a b to the power r in the expansion of bracket open a plus b bracket close to the power n. Notice the symmetry. N choose r equals n choose n minus r. That's why Pascal's triangle reads the same from left to right. Here's the big moment, the theorem itself. For any positive integer n, a plus b raised to n equals the summation from r equals 0 to n of binomial nr into a to the power n minus rb to the power r, or an expanded form, n choose 0 a to the power n plus n choose 1 a to the power n minus 1b plus n choose 2 a to the power n minus 2b squared, and so on, until n choose nb to the power n. That's a binomial theorem, the neat formula that replaces messy multiplication with elegance. Now, a great theorem deserves a proof. And the binomial theorem can be proved using mathematical induction. Step 1. Check the base case. For n equals 1, bracket open a plus b bracket close is clearly equal to a plus b true. Step 2. Assume it works for some n equals k. So bracket open a plus b bracket close to the power k equals summation from r equals 0 to k of binomial k r a to the power k minus r b to the power r. Step 3. Consider n equals k plus 1. Bracket open a plus b bracket close to the power k plus 1 equals bracket open a plus b bracket close into bracket open a plus b bracket close to the power k. Substituting our assumption, we get bracket open a plus b bracket close multiplied by summation terms. On distributing and regrouping, coefficients appear as binomial kr plus binomial kr minus 1. And guess what? That equals binomial k plus 1r, straight from Pascal's identity, so the theorem holds for k plus 1, completing the induction. Elegant, isn't it? Time for a worked example. Let's expand bracket open to x plus 3y bracket close raised to the power 5. Step 1. Coefficients are row 5 of Pascal's triangle 1, 5, 10, 10, 5, 1. Step 2. Apply the formula. Bracket open to x plus 3y bracket close to the power 5 equals summation from r equals 0 to 5 of binomial 5 r into bracket open to x bracket close to the power 5 minus r into bracket open 3y bracket close to the power r. Now compute term by term. For r equals 0, 1 times bracket open to x bracket close to the power 5 equals 32 x to the power 5. For r equals 1, 5 times bracket open to x bracket close to the power 4 into 3y equals 240 x to the power 4y for r equals to 10 times bracket open to x bracket close cubed into bracket open 3y bracket close squared equals 720 x cubed y squared. Continue this, and the final expansion comes out to 32x to the power 5 plus 240x to the power 4y plus 720x cubed y squared plus 1080x squared y cubed plus 810xy to the power 4 plus 243y to the power 5 dot, and there we have it, the full expansion. So, what did we learn today? We began with the need for a systematic way to expand powers of binomials. We discovered patterns in coefficients and exponents, explored Pascal's triangle, and defined binomial coefficients. Then we stated the binomial theorem formally, proved it using induction, and applied it to a real expansion problem. The key formula to remember: bracket open a plus b bracket close to the power n equals the summation from r equals 0 to n of binomial nra to the power n minus ab to the power r. And that's the foundation of the binomial theorem for positive integral indices. In the next video, we'll explore fascinating extensions like what happens when the power n is negative or fractional. Stay curious, and I'll see you there.